Okay, so we got air, and so we're going to think of this as an ideal gas. And it's a horizontal pipe. And so we're going to assume that the diameters are the same on both ends. And we're going to start with, I was just saying this to someone in office hours recently, like with these control volume entropy problems, you're almost always going to also use the first law in addition to the second law for control volumes. So to calculate these values, we're probably going to be using dE dt is equal to Q dot minus W dot plus M dot times, HI plus VI squared over 2 plus GZI minus M dot times HE plus VE squared over 2 plus GZE. Okay, and then we know that this is 0 because it's steady state, yes. And it's insulated, so we know this is 0. And we know that it's a pipe, it's rigid. We know that, we don't have any reason to believe that there's any work being done. So until I see different, I'm going to set that equal to 0.
Z should be equal to 0 too, because it's no change in height.
Yeah, horizontal, yep. And so the inlet and exit velocities. All right, well, I guess what we're going to use, did you say A?
Yeah, just A.
Okay, so I guess we're going to use M dot is equal to A V over little v. We know the areas. We know okay.
This is where I got started. I think what I
need
the mass flow rate to find the speed, but then you
need
the speed to find the mass flow rate.
Yeah.
And it's just a cycle. But
you're right. Okay, so let's see. So we got we know that the area that's going to be the same for both of them is equal to the velocity at the inlet divided by the specific volume at the inlet, and that's equal to a V exit over little v exit. These go away. So we can come up with ratios of these velocities depending on the specific volumes.
Then you can set up another equation. I think that's what I use the ideal gas law. Yeah.
So yeah, you can definitely use the ideal gas law to calculate those specific volumes.
We can relate the velocities by using, they're both equal to each other. So then, let me see. V1 is equal to 0.22.
Yeah, so you can come up with a relationship between those two.
You can plug them into the top in the first law.
Oh, okay. Huh. That would have taken me a while. Okay, so yeah, you can, so the ideal gas law says, so 600 kilopascals times VI is equal to 287 times 330. And so VI is equal to uh, 0.1435. And then at the exit, we have 120 times 10 to the third. V exit is equal to 287. Shoot, I used the wrong. Okay, so the first one should have been 330 there. So this is 0.1579, 0.1579. And then so little v exit is equal to 0.7175. And so VI times little v exit that we just found is equal to 0.1579 times v exit. So we'll think of that as like our first equation. And then we'll go to the first law for control volumes. So we can divide everything by m dot, and we get that HI plus VI squared over 2 is equal to HE plus VE squared over 2. And we know that we can calculate those enthalpies. So those are, so we can think of HI minus HE is equal to CP times the change in temperature, or I'll write that as TI minus TE. This CP for an ideal gas is R plus CV. I always write it the other way, I guess. Which is like around 718 plus, I think this comes out to be about 1005. And so HI minus HE is equal to 1005 in SI units times 30. So that's 30,150. So now these two together, so we have 30,150 plus VI squared over 2 is equal to VE squared over 2. And now we can plug in equation 1, express one of these in terms of the other one. So VE, let's say, is equal to 4.544 VI, and then you're set. So 30,150 plus VI squared over 2 is equal to 4.544 VI squared over 2, and then you can solve that.
Looks like my problem was I didn't cancel a word in the first law, so I just kind of got.
Oh, yeah. So you had extra variables in there. Yeah. Right. Right.
What did you get for MDOT?
Well, I haven't done that yet. But now that we have those, once you have those velocities, then you could plug that in here to get m dot.
Yeah, I did this like completely different.
Mm-hmm.
My answers are just like slightly under yours.
Oh, how did you do it?
I did like big V equals m dot little v over a.
Mm-hmm.
Solved for m dot, got the v's from the table. So I got like 1 meter per second and 6.9 meters per second.
And what do we get here if we solve it? Let's figure it out. Okay, so I think we get 30,150 is equal to 9.82 VI squared. And so VI is equal to 55. And so VE is that times 4.544. So 251.78 meters per second. And then we can use either one of those to find the mass flow rate. So the diameter is, so the radius is 0.006 meters. And so at the inlet, we have that the mass flow rate is equal to the area, 1.131 times 10 to the minus fourth, times the speed, 55.41, divided by the specific volume, 0.1579. And so I get 0.0397 kilograms per second. Okay. Well, let's finish this outline. So back to the outline from Friday. So we're still on part 1. We talked about the first law for closed systems, and then we talked about the differential form of the first law for closed systems, and the last thing is for part C. We have the first law for control volumes.
So is this right after heat transfer?
Yes.
Heat transfer was C.
Yeah, that was, it was?
That's what mine says.
Okay. So D then. And the first law, I'm starting to feel funny writing this so much, but might as well write it one more time. d dt for the control volume is equal to Q dot for the control volume minus W dot for the control volume plus Mi dot times the quantity Hi plus Vi squared over 2 plus Gzi minus Me dot times the quantity He plus Ve squared over 2 plus Gze. And when we do these problems, it's almost always in steady state. And so when it's in steady state, that means dE dt is equal to 0, and Mi dot is equal to Me dot, and you can just think of it as M dot. And then always the objective is to see what variables you can get rid of based on the assumptions. There are 2 lists that are important to remember for this, sort of keywords you can think about. The first one is Q dot is equal to 0 if any of these hold. And so that is, so first, if it says that the device is insulated. Second, if the fluid flow through the device is fast. Third, if there's a small surface area of the device. And fourth, if there's a small temperature difference between the inside and the outside. And so you can remember like that this one is if any of those hold, or you can just think, I think you can kind of reason out how that works. And then the second one, though, is how do you know when W dot is equal to 0? For this, it has to be all of these hold. The first one is that it's a fixed, rigid container device. So what that does is it means that there's no work of expansion for the material. Second, there's no electric power going in or out. And third, no rotating shafts. Like paddle wheels or something like that. And so that's the end of part 1. That's the end of the first law. And now we're going into part 2, the second law.
I have a quick
Yeah.
question about the Q dot. So in one of the homeworks that we just did, it was like the temperatures were like maybe 320 and 300 or something.
Uh-huh.
Would that kind of be one of those places where you'd say, okay, Q dot is negligible?
I mean, yeah, I think all of these, it's stuff like that. It kind of all comes down to, okay, so like if you saw that on a test and you made that assumption, you're like, that's a small temperature difference. And you would get reasonably good results no matter whether there was another way to do it or not. And I would give you full points on that.
Sure.
Yeah, but it's always just kind of a matter of whether there's a more accurate way to go about it or not,
Because I just got that far in the homework. I'm like, I can't figure out a way, so I guess I'll just say it's
Oh,
0.
yeah. Yeah, right. Right. Well, that's a reasonable thought process, and that would be perfectly fine. And if you couldn't find another way to do it, there's a good chance that that's how it was intended to be done, I would think.
Thank you.
Okay, second law of thermodynamics. So it starts with 3 equivalent statements. And they all have different uses. The first one is the Clausius statement. And really, the usefulness of the Clausius statement isn't mathematical at all. It's just to kind of ground yourself on that all of this comes from a very reasonable assumption that makes sense to all of us. This is just the one that says heat always transfers spontaneously from high temperature to low temperature. Second is the Kelvin-Planck statement. And that's the one, well, this one does have some mathematical uses. This is where we introduced the power, refrigeration, and heat pump cycles. We're going to get into power cycles in a lot more detail next. And in a lot of cases, you can use this to determine efficiency of cycles. So this is the one that just said, basically, any power cycle must lose energy to a low temperature reservoir. There has to be energy lost in the exhaust. And if you remember, the way it said that was you can't get work out of a power cycle with only one temperature reservoir. So you can't just have a hot thing pumping in heat and be going through a cycle and getting work out of it. There's no way to do that. You might think like we could make a perfect cycle where all of this heat is used to produce work and we don't need to get rid of any of that energy anywhere else, but it's not possible. And it's just totally derivable from the Clausius statement, which is amazing. And then third is the entropy statement. This is mathematically the most useful one. And it says, for an isolated system, the change in extensive entropy is greater than or equal to 0. What's the difference between an isolated system and an insulated system?
An insulated system just doesn't let heat transfer.
Yeah. That's the heart of it, exactly. So an isolated system allows no energy transfer across the boundary. Insulated means there's no heat transfer, but you could still have electrical power transferring across the boundary or mechanical power through shafts rotating. So this is just saying it's insulated and there's no other ways that energy is transferred either. Okay. Okay, so for the first part of this, there's not much more to say about the Clausius statement. So part A here is the Kelvin-Planck statement. And the way this cycle works, so let's start with a power cycle, and we'll do this for all three of these. So we have a high temperature reservoir and a low temperature reservoir. Heat transfers from the high temperature to our system. That's our QH. And so that's positive in the direction shown. And then QC leaves our system to the low temperature reservoir. And the result is that work comes out. And if you apply the first law to this cycle, taking into account the sign conventions here, you get that QH is equal to W plus QC. Efficiency for a power cycle, you can think of as the thing you're trying to get out of it, which is work. You're trying to maximize that. And you're trying to minimize the cost, which is the heat coming from the high temperature reservoir. And so there's our definition of efficiency. And then if you substitute in the first law, you can write this as 1 minus QC over QH. the maximum efficiency you can have for a given high temperature and low temperature reservoir is finite, and it's equal to 1 minus, just replace those heats with temperatures. Next is the refrigeration cycle. We have the high temperature reservoir, the low temperature reservoir. This time everything's going backwards. So we have heat leaving the system to the high temperature reservoir. We have heat entering the system from the cold reservoir. And in order to make this unnatural thing happen, we have to do work on the system, which in a refrigerator is the compressor. And so work is done. And now using this sign convention, the first law comes out exactly the same as it did because everything's reversed. And so again, we get that QH is equal to W plus QC. The performance of a refrigeration cycle is, we call it the Greek letter beta. And again, you can make sense out of how you define this. The thing we want is, I'll leave it like that. No, I have to make either one of these, I have to make these match. Let's call this let's call this QC instead of QL. So the performance, we're trying to get as much energy out of the cold part as we can. So that's our objective. And then the cost is the work that we're adding to this system. And if we substitute in the first law, we get QC over QH minus QC. And again, for the reservoir temperatures that you have, you can come up with an ideal performance coefficient by replacing the heats with the temperatures. And so you get temperature low over, oh God, I keep calling these different things. Instead of low, let's call everything C for cold. Now I think all those match. And now let's do that up here. Okay, so we have TC over TH minus TC. And then finally the heat pump cycle. The drawing and the first law are identical. To the refrigeration cycle. But we define the performance differently because we have a different objective this time. So we'll call it the Greek letter gamma. And what we're trying to do is get the most energy pumped into the hot reservoir. So our QH is our objective. And again, our cost is the work. Substitute in the first law, and you get QH over QH minus QC. And then replace all those heats with temperatures. And for a given set of reservoirs, your ideal performance is TH over TH minus TC.
So for ideal performance or the coefficients, and the actual performance not go over or under?
The actual performance is always under the ideal, yeah. For the power cycle, you can never get to 1 for these. For these other ones, you can go over 1. That's why they're not called efficiencies. But the ideal is always the highest, is always higher than actual. Okay, and then, so this was part A. Part B now is the entropy statement. And that's what we spend most of our energy on, time on. And first, remember that the definition of entropy is that the change in extensive entropy is equal to the integral from state 1 to state 2 of all of the heat transferred in across the boundary divided by the temperature at the boundary. And this is so this definition uses an internally reversible process. Then there are some other forms that are useful. And so when you have an entropy problem, it's always helpful to kind of think through, like, I have all these different ways of saying the same thing. Which one of, like, do any of these have the variables that I can use to get where I'm trying to go? So different forms of the second law. The first one, the Clausius statement, you can use as a form of the second law. You have to remember that this is only for cycles, though. So if an entropy question says something about a cycle, then there's a possibility that you're going to use this. And that says that over the cycle, if you take this same integral that we have in the definition over the boundary, it has to be less than or equal to 0. And equal to 0 means it's internally reversible. So you have to remember this time, this isn't for some idealized cycle. This is for the actual cycle that you're thinking about. And if you look at the definition of of entropy. It makes sense that this has to be equal to 0 for an internally reversible cycle, because a cycle means that your starting state and ending state are the same. And so if you're taking the integral from a boundary to the same boundary, you're obviously going to get 0. Then second, for a closed system, I gotta get going. Over a finite time interval. Oh, my stupid computer. Come on. We know that the extensive entropy is equal to the integral from state 1 to state 2 of dq over t around the boundary plus some sigma, and this is the entropy produced. And this has to be positive or 0. If it's 0, you know that the cycle is internally reversible, or the process is internally reversible. This is not necessarily a cycle. The Clausius statement is the only one that deals with cycles necessarily. And then the last one is for control volumes. And for this, we use a differential form. And this says ds dt.
It's big S, right?
Yes. Is equal to the sum of all the q dots over temperatures. The reason we're using a sum here instead of an integral is because of the mess of doing an integral with a differential form, and plus m dot at the inlet times the specific entropy at the inlet minus m dot at the exit times the specific entropy at the exit plus sigma dot. And this sigma dot again is, in this case, it's the rate of entropy produced. And again, this has to be positive or 0. And remember, as you do these questions, always be aware that the TDS equations might be useful. Just sometimes it comes up. And you can use those under any conditions. Okay, anybody have any questions about that? So that's where we are in the class right now. And the next thing we're going to do is talk about a specific type of power cycle and go into details about the different processes that make up this cycle. All right, that's all.